Today we want to look at waves, and waves are a fundamental part of nature. What's cool about waves is once you understand how one kind of wave works, like ocean waves and water waves, it applies to all the other types of waves. They have similar properties, including sound waves, earthquake waves, electromagnetic waves, etc. So let's break down what waves are. The first idea is that waves move energy across space and time. Waves are nature's way to transmit pure energy. And what's weird is when you see a picture of a wave, it's just sitting there, but you have to remember that the wave is alive, it's got energy, it's moving, and it's not static. Like in this photo, there's movement, there's energy. So waves travel across time and space is a way to think of it. And another way to visualize this is a wave transfers energy or information, like sound waves, internet, Wi-Fi signals, cell phone waves, etc., through space and time, but the key is they don't move any mass. So one example is when you play dominoes. You set up a string of dominoes, you knock down one domino, and it hits the next domino, etc., until you knock over, let's say, the 100th domino. So what's interesting is you can set up a wave through those dominoes, and you can knock down the last domino in the line without having to pick up the first one and throw it at the last one. Each particle disturbs the next one, and the disturbance propagates through space and time. Now, in terms of waves, there are two main types. There's mechanical and electromagnetic. We're going to focus first mainly on mechanical waves because it's a little bit more physical. You can see it better. And then we'll look at electromagnetic waves later on. Mechanical wave, by definition, requires a medium to travel through. So what do we mean by a medium? A medium just means some kind of substance it moves through. So for example, right now you can hear me because of sound waves. When I talk to you, I disturb the air inside my vocal cords. I don't know if you've ever tried this, put your hand on your throat and talk. And then that shakes the air in my vocal cords, which then shakes the air in my mouth, and then the air molecules, kind of like dominoes, continue to hit each other until eventually it gets the air by your eardrum, which then shakes this thing called the cochlea, and then your brain turns that into electrical signals, and you say, aha, I hear something. But I don't actually push air into your ears, because that would be kind of gross. That means whatever I had for lunch or breakfast or dinner might end up in your ears, and that's just nasty. So the big idea is something has to move through, rather mechanical wave has to go through medium. And in real life, there are many types of mechanical waves. Obviously, water waves in the ocean. This is a little Red Bull extreme surfing clip I linked to on this Prezi, so you can explore this later. It's really fun. These guys are totally crazy. Earthquake waves, obviously. We've had some major earthquakes recently there, and knowing some of these properties can help us design safer bridges, buildings, etc. Oprah in 2009 was really neat. There was the Black Eyed Peas performing, and then suddenly a flash mob appeared out of nowhere, and you can see in this clip later on there was a very synchronized demonstration of wave properties done by a mob there. This artist named Ben Hughes was trying to experiment to visualize sound waves using soap bubbles and paint and all that with some funky techno music. So something neat to check out later on there. The other main type of wave, besides a mechanical wave, is an electromagnetic wave. And the key idea to an electromagnetic wave, EM for short, is that it's pure energy. No medium is required whatsoever. And actually, this is only something discovered in the last 120 years or so. Before this famous experiment called the Michelson-Morley experiment, and if you want to look it up for a little bonus and do a little mini research paper there, scientists thought there was this thing called the ether that surrounded the Earth in outer space. And in order for electromagnetic energy from the sun to get to Earth, they thought there had to be this invisible substance that fills outer space that's perfectly dense but has no weight or something strange like that. And so what famous Michelson-Morley experiment by these two famous scientists, they basically proved there is no ether, so it's kind of weird. And they actually won the Nobel Prize for that. It was one of the first American Nobel Prize winning experiments, which is kind of funny. They're just basically proving there is no such thing as the ether. But anyhow, electromagnetic wave is basically pure energy. You take an electron and you jiggle it, and by doing that, you generate a whole range of frequencies, and we use that in real life, whether it be radio, microwave, internet's in that range there. So if you're surfing the web right now, you shake an electron fast enough and eventually it gives off what we call infrared energy, which shows up on a infrared camera as heat signature. Then finally a little tiny sliver is what your eyes can finally pick up. Then ultraviolet X-rays used by doctors, and then gamma rays is high intensity radiation. And we actually harness all of these with our technological tools to our advantage there. But ironically, your eyes, you can almost think of yourself as being colorblind. You only see less than 0.1% of the entire electromagnetic spectrum that's out there. In terms of the two main types of waves, they have similar properties. And again, once you understand one type of wave, it applies to any wave. So in terms of the basic properties of waves, there are two main types of waves that we can define. The first one is called a transverse wave. A transverse wave, simply by definition, is the particles of the medium vibrate perpendicular to the direction of travel. So notice here on this string, in slow motion here, this is really cool. The wave goes, let's say, front and back across the room here, but the particles of the string actually vibrate up and down. So notice that even though the wave travels front to back, the particles go perpendicular up and down to the direction of travel. In some ways, a simple string being snapped up and down is a way to visualize that. Now contrast that to a longitudinal wave. By definition, a longitudinal wave is a mechanical wave in which the particles vibrate, instead of perpendicular, parallel to the disturbance. So notice the wave travels left to right here, and the particles also vibrate left to right. Sound is a good example of a longitudinal wave. Why is that helpful to know? Well, in real life, if you know how a wave is behaving, you can design things for that purpose. So for example, for sound waves, it's useful to know that it's a longitudinal disturbance. If you're designing a musical instrument and you want to tune it right, or you're trying to build a concert hall and not have too many echoes, etc. Finally, some basic wave characteristics. We call the resting point, where the wave is just sitting there, the equilibrium line. So this could be like the string just sitting there still, or an ocean wave just sitting still and there's no disturbance. Once you put energy into the wave, then you can generate a high point called a crest, a low point called a trough. The distance it takes a wave to repeat itself is called a wavelength. And the symbol we use, we run out of letters in the English alphabet, so it's the Greek letter lambda. It looks like an upside down Y, is a symbol we use for wavelength. So notice I could go crest to crest, would be one wavelength. I could also do trough to trough, or if you think of your math class, I could pick a sine wave where I go from 0 point to 0 point. So think of it like a roller coaster. Once you repeat yourself, the ride is repeating itself. That's a wavelength. The amplitude is a maximum distance from equilibrium, and it's a measure of the wave's energy. So obviously, if you're surfing, you try to hit big waves, like in Maui. So the amplitude is a way to measure the wave's energy. Now we can define these wave characteristics with a couple of standard symbols and then tie in some basic equations. So, like we talked about before, wavelength, we use the Greek letter lambda. The metric unit will be in meters when we want to measure the size of a wave. So one thing that's interesting as a little bonus project would be check out the size of the radio antenna on top of the school for our radio station. I think we're 88.5 WHSD, which is 88.5 megahertz. And I bet the wavelength of the broadcast frequency, 88.5 megahertz on the FM dial, is pretty close to the size of our antenna on top of the school there. The period is a time for one cycle of the wave to generate itself. So the inverse of the period is what we call the frequency, the letter F. And it's the cycles per second, and we just call that the hertz. Not to be confused with a rental car company, but in honor of a German scientist who did a lot of studies with waves, in honor of Hertz. So HZ is the abbreviation. So maybe one example is if you have a cordless phone. In the old days, we had 900 megahertz cordless phones, and we have 2.4 gigahertz, and now there's 5.8 gigahertz. And all that means is, in your cordless phone at home, the electrons inside that antenna will jiggle 5.8. Giga means billion times per second. And so basically, the higher the frequency usually means higher energy, so usually it's a clearer phone call. That's the way to think of it. You might have seen those terms too if you're shopping for computer stuff, like the speed of a processor, like an Intel Quad 4 2.8 gigahertz processor. And all that means is the computer's clock jiggles back and forth the electrons 2.8 billion times per second. Finally, we can come up with what we call the wave velocity equation, which is the speed of how fast the wave is going. Now, speed is just distance over time. In fancy physics words, speed we want to call, instead of just speed, we use velocity, because velocity is a better definition. It's speed with direction. So if you recall, velocity is your change in displacement over time, your distance over time. But another way to look at that is it's your wavelength times frequency. Instead of distance, we're going to use wavelength. And instead of time, time is 1 over the frequency, or frequency is 1 over the time. So in other words, if you look at the units here, we have meters, and then frequencies in hertz are 1 over seconds. We get meters per second. So maybe another way to look at that is if you think of a runner like a sprinter, like Usain Bolt, we could figure out how fast Usain Bolt is running to set another 100-meter world record by just taking distance over time. But another way to look at it is to think of Usain Bolt as a wave, which is kind of weird. And the way you can think of that is he's such a fast sprinter because he has a long stride length. That's like his wavelength. And then the frequency is how often he can repeat the cycles of running, how quickly he can move his legs. So he can move his legs 5 times a second. That would be a frequency of 5 hertz. 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. The period would then just be 1/5 of a second if we wanted to solve for that. So in other words, it takes 1/5 of a second, 0.2 seconds, for him to have 1 stride, would be the way to look at it there. So in a nutshell, we just wanted to tie in for you the basic property of waves in terms of the 2 main types, mechanical and electromagnetic, some examples of each of these types of waves and some of their basic properties. So for this next unit, this is a foundation for defining some of the basic terms when it comes to wave properties. And there you have it.